Lagrange multipliers are used to find the maximum and minimum values of a multivariable function when you have a constraint of another function. It's used a lot in differential equations, so this is kind of your introduction to it. So there is a lambda, and this is the Greek letter lambda, and it's used as a special character. It is called your Lagrange multiplier. So it is literally your Lagrange multiplier. It was developed by the French-Italian mathematician Joseph Louis Lagrange, who lived in the 1700s and was quite a mathematician. So this is the method of Lagrange multipliers. So to find maximum and minimum values of a function with more than one variable, subject to a constraint of another function of more than one variable. Now notice that your partial derivatives of g can't be zero. Then you're going to find the the gradient of f equal to lambda, the gradient of g, and we're going to let g equal to k. So we have a surface g and a surface f, and we're going to do all that. Now letter B says evaluate f at all the points. The largest is the maximum value, and the smallest is the minimum value. So the important thing here is your lambda, and we're going to walk through a couple of them. Your book goes through a nice geometric explanation as to how this works, but it uses the gradient and the gradient of both the equation and the constraint. So as we use this, after we find them, then what we're going to do is we're going to take the partial of f with respect to x and instead of equal to lambda partial g. We're going to take the partial of y instead of equal to lambda g sub y. We're going to take the partial with respect to z of f and instead of equal to lambda, the partial with respect to the partial of g with respect to z. And then we're going to take g instead of equal to k. So we're going to use all of these to solve for lambda. And when we solve for lambda, we'll be able to solve for our maximum and minimum points. It'll make sense. It's not overly difficult, but the key is these lambdas happen in here and setting these equations equal along the way. So it says find the extreme values of the function on the circle with these. This is the constraint. So here you have f of xy is this equation, and this is going to be g of xy here. So it's equal to 1 and all of that. So that tells us that our k is 1. We're going to start with the gradient of both. So we're going to start with the gradient of f. So let's do the partial of x is 2x, and the partial with respect to y is 4y. So the gradient of f is equal to the vector 2x, and the second component is 4y. Now let's talk about g. The partial derivative with respect to x is 2x, and the partial derivative with respect to y is 2y. So the gradient of g is equal to 2x, and the second component is 2y. Now the Lagrange multiplier says that our gradient of f is equal to lambda, the gradient of g. So we're going to say 2x, 4y, that vector, is equal to lambda times the vector of 2x, 2y. Now we could distribute that lambda in there, but we tend to say that the first component has to be equal to the other. So we're going to say 2x equals lambda times 2x. And our second equation is 4y equals lambda times 2y. You remember our third equation is g of xy, which is x squared plus y squared is equal to 1. In this case, k is 1. Now we're going to take this. These are our equations that we're going to work with that come from our steps that we looked at last screen, the method of Lagrange multipliers. Couldn't remember what it was called. So we're going to look at these equations. We're going to solve for lambda and x and y, meeting these requirements. So let's take the top one, and we have 2x equals lambda times 2x. We can call it 2x lambda, 2x lambda. Now, remember you can never divide by your variable, so you could divide by the x, but that's not super helpful. So let's move this to the other side. So we have such, and let's factor out the 2x. So we have 1 minus lambda equals 0. Now, based upon factoring, we know that 2x equals 0 and 1 minus lambda equals 0. So x equals 0 and lambda equals 1. Now, what this tells us is these are the possible places where extreme values happen. Now, let's take that x equals 0 and plug it into x squared plus y squared equals 1. So then we get 0, so we get y squared equals 1, so y equals plus or minus 1. So when x equals 0, we have the point 0, positive 1, and 0, negative 1. Now let's take our lambda and let's go back up to the y equation. Since lambda equals 1, then we're going to say 4y equals lambda times 2y. So if we put lambda equals 1 in there, we end up, I would like to subtract first. 4y minus 2y lambda equals 0. And since lambda equals 1, we get 4y minus 2y equals 0. 2y equals 0, and y equals 0. Now that we know that y equals 0, let's put that into x squared plus y squared equals 1. So x squared equals 1. So x equals plus and minus 1. Hopefully that wasn't too difficult to follow. So that means that we have plus and minus 1, 0. So what that tells us is that we have 4 points with extreme values. We have 0, 1, 0, negative 1, 1, 0, and negative 1, 0. These are our 4 points with our possible extreme values. So we're going to say possible extreme values. In order to determine if they are extreme, we want to find f of x. So let's f of xy. So let's remember that f of xy is equal to x squared plus 2y squared. So we're going to plug each of them in. So we're going to say f of 0, 1 is equal to 0 plus 2, which is 2. F of 0, negative 1 is equal to 0 plus 2, which is 2. F of 1, 0 equals 1 plus 0, which is 1. And f of negative 1, 0 equals 1 plus 0, which is 1. So our maximum values are these two values right here. So we can say that we have maximum values at 0 plus and minus 1. We could be more specific and say we have maximum values at 0 plus and minus 1. And the maximum value is 2. And we're looking at the maximum value of f on the circle x squared plus y squared is 1. So here you can see figure 2 is your f of x with your g of x on it. And figure 3 is the contour map, and it kind of shows the geometry happening. This is a very cool graph. In figure 2, you can see the circle x squared plus y squared equals 1 and the way it travels around. So we have maximum values occurring at 0, positive 1, and 0, negative 1. We did this problem in the last section, but we get to do it again in terms of Lagrange multipliers. So it says a rectangular box without a lid is to be made from 12 meters squared of cardboard. Find the maximum volume of such a box. So we're going to start with the volume. Let's let the volume be XYZ, just like we did before. Now think about this box as if we haven't already done it. I probably should see if there's like a box tool to make it draw more concisely, to make it draw better. But it's okay, I like my box. So I'm going to put X, Y, Z, just like I did before. Now it does not have a lid, so our surface area is equal to this piece here is X, Y, I'm sorry, X, Z, and there's two of them. And the front is YZ, and there's two of them. And the top is XY, and there's only one of those. And we know it's equal to 12 meters squared. So do you see how this is our constraint right here? This is our G of XYZ because it has It has an equal value, so it's our constraint. So this is our f of xyz up here. That's what we're trying to maximize. And then g is our surface area. So I'm going to rewrite it to say, let's let f equal xyz, and let's let g equal 2xz plus 2yz plus xy, which is equal to 12. So let's find the gradient of f, and I'm just going to go ahead and do it in the form here. So when I take the derivative with respect to x, I get yz. When I take the derivative with respect to y, I get xz. When I take the derivative with respect to z, I get xy. Okay, so now let's look at the gradient of g. So the derivative with respect to x is 2z plus y. The derivative with respect to y is 2z plus x. And the derivative with respect to z is 2x plus 2y. Now, the Lagrange multiplier says we're going to say the gradient of f is equal to lambda times the gradient of g. So let's look at and we also need to look at g is equal to 12. So that's going to be our equations. Now there are three parts to the gradient of f and the gradient of g, which is important. They have to have the same number of components. So we're going to say the gradient of f is yz, xz, xy, and this is equal to lambda times the vector 2z plus y, 2z plus x, and 2x plus 2y. Let's go ahead and write our g is equal to 12. So we have 2xz plus 2yz plus xy equals 12. It doesn't matter when you write it as long as you write it. Now we're going to write our equations component-wise. So we have we have yz is equal to lambda times 2z plus y, and xz is equal to lambda times 2z plus x, and then xy is equal to lambda times 2x plus 2y. Now, if you look at these, they really don't share a whole lot. You could solve for z in the first one, but let's be a little creative and do it a little bit differently. You don't have to be creative about it, but I can kind of see that it would be easy to have xyz on the left side of each of these. So let's multiply this by x. So we get xyz is equal to lambda x times 2z plus y. I'm going to fill in y in a minute. I'm going to come back to the reasoning in a minute. Let's multiply this one by y. So we have xyz is equal to lambda times y times 2z plus x. And this one, xyz, is equal to lambda times z times 2x plus 2y. Now, if I multiply this out, we have xyz is equal to 2xz lambda plus xy lambda. Sorry, that took me a second there. Here, xyz is equal to 2yz lambda plus xy's lambda. Notice those are very similar for both of those. And this says xyz is equal to 2xz lambda plus 2yz lambda. Now, on a general case, this lambda could end up to be 0. But if we come back over to here, if lambda is 0, then all of these are 0 because the right-hand side would be 0 times anything is 0. So lambda should not be 0. But now that we have xyz equal over here, these equations, then we can set them equal to each other and begin to solve. So let's take the top two, and let's say 2xz lambda plus xy lambda equals 2yz lambda plus xy lambda. So we set the top two equations equal to each other. Now we have a lambda everywhere, and it is not a good idea to divide by your variable, but in this case, we're going to divide by lambda. So we have 2xz plus xy equals 2yz plus xy. You just threw out the possibility that lambda could be 0. So you don't want to do that regularly, but we'll solve for lambda in a different way. Now, if we get here, we could subtract xy from both sides. So we get 2xz is equal to 2yz. Now, you can't divide by z. It's not a good plan. So let's move them to the same side. So we have 2xz minus 2yz equals 0. If we factor out this, let's factor out the 2z, and we get x minus y equals 0. So z equals 0 or x minus y equals 0, so x equals y. Now, if z equals 0, we have a volume of 0, so let's throw that out. And so we're going to keep the x equals y. And let's take that and plug it in. Well, before we do, we didn't actually eliminate a variable. So we use these top two equations down here. So let's work with the next two equations. And let's say 2yz lambda plus xy lambda is equal to 2xz lambda. My lambda looks a little funky. Let's try it again. Plus 2yz lambda. Now, again, we're going to say that lambda can't be 0, because if it is, what we could do is we could do like we did before and bring everything to the left-hand side and factor out the lambda and say lambda equals 0, but that can't happen because that would lean towards the volume of 0. So we're going to say lambda is not 0 and take the lambdas out of the equation. So we have 2yz plus xy equals 2xz plus 2yz. Again, we have 2yz's on both sides, so I want you to see that these cancel out. So we end up with xy equals 2xz. If we let's bring the xy over. 2xz minus xy. Let's factor out the 2, or just the x. And we have 2z minus y. So from that, we would get x equals 0, which gives you a volume of 0, so that can't happen. And then we have 2z minus y equals 0. So y equals 2z. So we have x equals y over here and y equals 2z. So we know that x equals y equals 2z. The reason we had to do the blue with two equations up here is because we didn't end up with x equals a number. If we did, we might could have put it in and solved it differently, but we did not. So now we're going to take that and put it into our constraint equation. And our constraint equation was G, and it said, so our constraint equation was G of x, which we have, is 2xz plus 2yz plus xy equals 12. So let's put 2z in for everything rather than dealing with fractions. So in place of x, I'm going to put 2z. So 2 times 2z times z makes 4z squared. Plus, in place of y, I'm going to put 2z. So again, I have 4z squared. Plus, x times y is 2z times 2z, which is 4z squared equals 12. So if we add these up, we get 12z squared equals 12. So z squared equals 1. So z equals plus and minus 1. So if z equals positive 1, remember that you can't have a negative because we're working with the side lengths of a box. So z equals 1, that means that y equals 2 and x equals 2. So the maximum volume of the box is 221. We don't really have to check the maximum because it's the only one we found, so it must be the maximum, but we could plug it in to check it if we wanted to. So this shows you how to use the Lagrange multipliers if you have a constraint and you have a function and then you have a constraint as well. another surface with the constraint. It might be a little easier. You might like it, you might not. At least it's not too hard. It is systems of equations. It is used greatly in differential equations, so go ahead and learn it now. I could do one more of these for you, but I think that you get the idea. And so I'm going to go ahead and close out this video because the only homework I gave you was what we went through was using Lagrange multipliers to find your extreme values given one constraint. So I hope you enjoy this lesson.